But anyway, so I'm going to talk about something, the research we are doing with solar and wind power to drive hydrogen production. I'm from Arizona State University. How to go to next slide? It does not move. Oh.
Can you click the arrow key on the keyboard?
Yeah. Okay, it's just yeah. Okay. So this work is supported by National Science Foundation, and also I have a little bit funding from Salt River Project. That's a utility company in Arizona. And also, fortunately, I have some really, really good students, Joe, Kevin, Adashia, and with the time I have, I will be focusing on two things. One is the emissions of various power sources for hydrogen production. That's the motivation for solar wind power, the electrolysis. And that also leads to a definition of a clean grid based on hydrogen production. Then I will present a techno-economic analysis to look into the energy losses in different power delivery options. And then I will propose probably the most efficient, the lowest cost system layout for hydrogen production. We all know that hydrogen is produced from fossil fuels today, and in the US, we use natural gas to produce the hydrogen. So the CO2 emission is about 12 kilograms CO2 per kilogram hydrogen. So anything we do, yeah, I have the. Yeah, all the animation does not work here, but yeah, okay, I just do it without animation. Okay, let's go to the next slide. So now, in my hydrogen center, we cover 3 hydrogen production technologies: water electrolysis, methane pyrolysis, and solar photocatalysis. Today, I'm going to focus on water electrolysis. Now, if we look at the CO2 emission by electrolysis, electrolysis itself does not emit CO2, but it takes a lot of electricity to do electrolysis. I think the most widely accepted number is about 60 kilowatt hours of electricity for 1 kilogram hydrogen. And the problem is that in most parts of the world, the grid is quite dirty. In the US, the average CO2 emission for grid power is 0.39 kilograms CO2 per kilogram hydrogen. So if you multiply the two numbers, we end up with 23 kilograms CO2 per kilogram hydrogen. That's twice as much as steam methane reforming. So that's not something we should really do. And so this gets into, before I talk about what else can we do, and let me first talk about how to define clean grid. Since we can emit no more than 12 kilograms CO2 per kilogram hydrogen, and we need 60 kilowatt hours electricity for 1 kilogram hydrogen, so we divide two numbers, we end up with 0.2 kilograms CO2 per kilowatt hour. Now, this is the break-even point. If the grid is below this level in the US, we can plug in our electrolyzer, then we do no harm, no benefit to the environment. If we further reduce this, then we will draw environmental benefits. So let's see if we reduce this number to 0.1 kilogram CO2 per kilowatt hour. That means we need to cut down the CO2 emission of the US grid by about 75%. That will take many decades to realize. Yeah, it does not advance its own. So what else can we do now? In most parts of the world, I can say Norway is the exception, the Sweden is the exception, but in most parts of the world, we have to integrate low carbon power sources directly with electrolyzer, like solar, wind, hydro, or even nuclear. And if we look at the CO2 emission for solar powered electrolysis, I did this calculation myself. It's about 2.3 kilograms CO2 per kilogram hydrogen. For wind-powered electrolysis, I took a number from a paper, and it's 0.68 kilogram CO2 per kilogram hydrogen. So these really are the environmental motivation for low carbon hydrogen production. Now, so we need to use solar, wind, also hydrogen and nuclear are also possible, but the hydrogen has been demonstrated for almost 100 years now. Nuclear, I also saw some recent report from the US Department of Energy. So the difficulty is really with solar and wind. Now, some of the issues involved, one is the power sources are not intermittent. So how can we operate a electrolyzer with intermittent power sources? Then also intermittency typically accelerates the degradation in the electrolyzer. So how can we minimize the degradation? A related challenge is the low capacity factor. That's part of the reason why low carbon hydrogen is expensive. The average capacity factor for wind farms in the US is 35%, solar farms 24%. So the question is, how can we improve the capacity factor? Now here, I don't believe we should use the energy storage device, because once we use energy storage device, the levelized cost of electricity doubles. So that's really against the goal of low cost hydrogen. So what we should do is to integrate multiple low carbon power sources into an electrolyzer. Now, if we talk about multiple power sources, for electrolyzer, that introduces another set of challenges. One issue is that now we have both DC power and AC power in the same system. So solar produces DC, and wind, hydro, nuclear generates AC. So where the system can handle both DC, AC power efficiently. Then there's also an issue of order in power consumption, because we have multiple power sources. Which power should be consumed first, which one second, which one third? We want a most efficient system here. Then also another issue is how to deliver DC power to a DC load, because for the last 150 years, all the megawatt power sources are AC sources, so are used to AC power delivery. So this is the first time we have megawatt DC source, and we have megawatt DC load, and we have to rethink everything we take for granted about the power delivery. Then there's also the question of we have multiple power sources. They are not always in the same location. So the question becomes, where should the electrolyzer be located? So the highlighted parts are the question I hope to answer today, but we do work on other questions as well. Now, just to remind everyone that we do electrolysis today, and several raw materials are produced. Excuse me. Okay, and several materials are produced electrically today, like chlorine, caustic soda, aluminum, copper. We produce like tens to even 100 megatons a year. So all these electrolyzers are megawatt electrolyzers. So how do we power them? Now, this is a lot of power into a very small footprint. And the whole ASU campus is about 30 kilometers by 30 kilometers. We use average like 85 megawatts on average. But a 100 megawatt electrolyzer is probably smaller than the size of one building on ASU campus. So it's a very concentrated power demand. And so the way we power them is they all take a high voltage from a grid, say at least 100,000 volts. It could even be 500,000 volts. Then once the power reaches the electrolyzer, there's a step-down transformer, sometimes a step-down transformer for each stack. And so those transformers are maybe 10, 20 megawatts each. Then we do rectification to convert the low voltage AC power, typically around 500 volts, to DC power. But the current is enormous, and 100,000 amps per stack is often you can see that. Now, so the point here is that all the power devices for AC powered electrolysis, transformers, rectifiers, circuit breakers, they are all commercially available. Now, this is just a little bit of background knowledge before I get into the techno-economic analysis. And each time we have a power conversion, there's a cost for the power device, there's energy loss in the power device. So power conversion should always be minimized if possible. Then in this case, we will have both AC conversions and DC conversions. AC conversions such as AC to AC through transformer, AC to DC through rectifier, they are typically much more efficient than DC power conversions. So here I use the number 3% for each AC conversion. For DC conversion, and it's 10% for each conversion. And because DC conversion is based on transistor switching, so DC to AC inverter or DC to DC charge controller or maximum power point checker. Looking into solar wind powered electrolysis, and the goal here is to minimize energy loss and in power delivery between the solar farm or wind farm to the electrolyzer. So we need to look at the options for power delivery. We can deliver the power through AC, we can deliver the power through DC. Also, the distance between the power source and electrolyzer is off our control. So if they are far away, then we need two more power conversions to step up the voltage, and then once it reaches the electrolyzer, to step down the voltage. If they are co-located, then we can get away with a low voltage. So there are too few power conversions if they are co-located. So now we can look at different power sources. For wind power, if the distance between wind farm and electrolyzer is far, then we need 3 power conversions plus cable loss, and a step-up transformer, let's say 97% energy efficiency, cable loss, let's again assume 97% efficiency, a step-down transformer, 97% efficiency, then rectifiers, 97% efficiency. Those are the 4 energy losses in long-haul wind power delivery. Now, if the wind farm and the electrolyzer are co-located, then we don't need high voltage, so we can take out the transformers, but we still need a rectifier with 90% efficiency, and then cable loss 97% efficiency. So if we calculate the system energy delivery efficiency for long-haul wind power, it's about 89%. For co-located wind farm and electrolyzer, it's about 94%. So we lose either 6% or 11% of the wind energy. Now, if we look at solar, that's really a lot of challenges or opportunities are. And there are 3 options, and we can do AC delivery, so we do DC AC conversion, then AC DC conversion to deliver power. We can also do DC DC conversion with DC DC converters. We can also do direct coupling. But today, there's only one option. Let me show you. Today, the only way we can power a megawatt electrolyzer with solar power is through AC. There's no other way of doing it. And in Japan, they commissioned a 10 megawatt electrolyzer about in 2020. That's coupled through AC. And so what we need to do is we need to first, on the solar side, we need to do maximum power point tracking. And then if it's a long haul power delivery, we need a step up transformer. And first DC AC conversion, then a step up transformer. And then once it reaches the electrolyzer, a step down transformer and a rectifier. So we can see how much energy loss there is in this case. A 10 megawatt electrolyzer powered by solar. And if we do AC coupling long distance, we need a 40 megawatt solar array, solar system. And then we need 5 solar arrays, each at 2.8 megawatts peak to add up to 40 megawatts total. The reason is that the size of the inverter is limited. You will not be able to find a 40 megawatt inverter, and the 30 megawatt is probably as large as you get today. So that's why we need 5 solar arrays. Then after maximum power point checking, we lose 10%. After inversion, we lose another 10%. So after the inverter, 14 megawatt becomes 11 megawatt AC, 11.3 megawatt AC. Then we have all the AC conversions, step-up transformer, step-down transformer, cable, rectifiers. Total, they lose about 11% of the energy. So after AC conversions, 11.3 megawatt AC become 10 megawatt DC. So you can see we started with 40 megawatt DC. Now we end up with 10 megawatt DC. So 4 megawatts is just lost in all the power conversions. Let's see. Okay, here. Yeah, if we do co-location through AC, then we don't need high voltage, so we can get away with a 500 volts, 600 volts, but we still need to do maximum power point checking. That's 90% efficiency. We still need to do DC AC conversion, 90% efficiency, cable loss, 97% efficiency, rectifier, 97% efficiency. So if we calculate the system energy delivery efficiency for long-haul AC, it's about 72%. For co-located AC delivery, it's about 76%. So we lose roughly about 25% of solar energy. Now, if we do DC delivery, in principle, people would think DC power source, DC load, so DC conversion should be more efficient, but in reality, it's actually not. Now, yes, we have fewer power conversions, but they involve DC power conversions, so that's why they're not. You can see in the end, it's a very complicated, expensive system and with similar losses. The main issue is that DC power converters have a very limited power rating or current rating. A single power transistor can handle roughly about 50 amps, but the largest electrolyzer stack now exceeds 10 kiloamps. So we basically need more than 200 power transistors in parallel to drive that electrolyzer. That's really expensive and poor reliability power management system. So now, but even say we can develop a power transistor which can handle 10 kiloamps, let's see whether it's more efficient. So that's the other argument I have. I don't believe we need to even bother with DC power converters. Now, if we increase the long haul DC power delivery, we need 30 power conversion, we need to maximum power point checking, we need to DC conversion from low voltage to high voltage, so that's 90% efficient, maximum power point checking, 90% efficient, cable loss, 97% efficient, and once the power reaches electrolyzer, we need another DC conversion to get a low voltage, so that's 90%. So you can see how much loss is there. If they are co-located, then we just need to do maximum power point checking, 90% efficient. We still need to do one step of DC conversion for voltage control. That's 90%, and cable loss 97%. So if we look at the DC coupling cases, the energy delivery efficiency is 71% for long haul DC and 79% for co-located DC. So they are not noticeably better than AC coupling. So in terms of efficiency, there's no significant gain. And in terms of complexity, cost of the system, they are really expensive. So then plus that, they really don't support a megawatt electrolyzer. So that's why I don't think a DC converters is a good option for hydrogen production. Now, so this gets into the next question. What should we do if we don't want to go through the AC coupling? Now it works. Okay, good. The other option is direct coupling, because it's DC source or DC load. So as long as the voltage matches, as long as the power matches, we can directly connect the cables from the solar array to the input terminal of the electrolyzer. Now, of course, we need to properly design the solar array or the electrolyzer stack so the voltage matches the power matching. But that's direct coupling. If we look at a direct coupling, there's zero power conversion. And so that there's no energy loss due to power conversion. There's no cost for the power device, except we probably still need some circuit breakers. But there's a 9% energy loss due to the fact that the maximum power point is not being checked. There's a very nice paper published almost 40 years ago, which analyzed it. But even with 9% energy loss plus another 30% cable loss, that's still the best system we can have. And because it's more efficient than any other system and lower cost than any other system I have discussed. So here is a comparison of the system energy delivery efficiency with the derived coupled system. We have 91% efficient because we're not doing maximum power point checking. Then we have 3% cable loss, but we don't have anything else. So the total delivery efficiency is about 88%. This is better than all the AC coupling and DC coupling. Now here I took out all the DC coupling because they only support kilowatt electrolyzers. So that's why I don't think they are even need to be listed here. So derived coupled system is more efficient than the system through AC or DC delivery. Now the last part is what we call load matched system. And this is really our research. We are adding innovation to a derived coupled system so we can improve the efficiency of maximum power point checking to more than 99%. And we still have 3% cable losses. So that's why we end up with 96% energy delivery efficiency. So I don't have time to talk about everything here, but the key innovations that we're adding to derived coupled system is that we can do maximum power point checking without any power converter, and we do it by load matching. That delivers about 99.5% solar energy to the electrolyzer stacks compared to about 75% for any current systems. And then also without the power device, the upfront system cost is 15% lower than co-located system and 30% lower than long haul power delivery. And also it has excellent scalability and reliability because the power converter really defines the system power. But now we take out the power converter, so we can go from about 1 kilowatt all the way to several hundred megawatts easily. And also there's no failure of the power converter in this system, so the system is more reliable. So if we look at the innovation, we do maximum power point checking without the power converter. Also, we do maximum current point checking instead of maximum power point checking because for hydrogen production, it's the coolants, not the joules, which matter more. Then also we integrate multiple power sources in hope to achieve 100% capacity factor. So coming down to 100% capacity factor. Now, based on there are basically two issues here. One is with multiple power sources, what's the order in power consumption? The second question is where the electrolyzer should be co-located if the power sources are not co-located. And so based on the techno-economic analysis, if we want the most efficient system, lowest cost system, this is the system layout. This is our proposal. That is, the electrolyzer should always be co-located with solar farm. That's the only chance we can get a 4% solar energy loss. Then also all the solar energy should be consumed in real time for hydrogen production. No solar power to the grid, because anytime you send solar power to the grid, we lose 25% solar energy. So that's solar are consumed locally for hydrogen production to achieve a 4% solar energy loss. Then wind farm, if possible, we should co-locate that with the solar farm, but often that's not possible. So the difference is that we either lose 6% of wind energy or 11% of wind energy. But the wind is supplemental to solar for hydrogen production. If there's not enough solar for hydrogen production, we bring in wind. But if there's more wind energy than what we need, excess wind goes to the grid. Now this is AC power to AC grid, so there's no additional energy loss. Then hydro and nuclear, now of course they are most likely will not be able to co-locate them, but they are supplemental to solar plus wind. So if there's not enough solar, not enough plus wind, then we bring in hydro or nuclear. So because the capacity factor of solar is 24%, and let's assume that we get another 25% from wind. So solar wind can provide about 50% on energy. So we just need the other 50% from hydro or nuclear. So here is the system layout we have in mind. So everything here in the dotted box are co-located. The electrolyzer stack, the PV array, the step-down transformer to rectify, they are located with electrolyzer. Then now here we assume wind is far away and the hydro is far away, nuclear is far away. So they all need a step of transformer to deliver the power to the electrolyzer. Then after step down, and we supply power to the electrolyzer. So in this case, the energy losses for nuclear, hydro, and wind are all 11%, and for solar it's 4%. So coming down to the last slide, we can plug in an electrolyzer if the grid is below 0.2 kilograms CO2 per kilowatt hour. Now, of course, that's in the US. If it's in a country where electricity is largely produced from coal, then this number is 0.4 kilograms CO2 per kilowatt hour. Now, if the grid does not meet this emission requirement, then we have to integrate multiple low carbon power sources directly with electrolyzer, bypassing the grid. Come on. I have another animation. It does not show up here. Okay. Yeah, okay, it's not sure. I have to explain to you. So basically, when we have multiple power sources with a electrolyzer, it's basically a co-located solar electrolyzer, co-located derived coupled solar electrolyzer. Then it's backed by wind, and then it's further backed by hydro or nuclear to approach a 100% capacity factor. I think that's the last slide I have. Yeah, that's the last slide I have. So thank you very much, and I'll be happy to answer questions or discuss any topics of interest to you. No. So yeah, it's just slow. Yeah, what the electrolyzer for low carbon hydrogen production is basically a solar electrolyzer backed by wind and further backed by hydro and the nuclear. Yeah.
Thank you, Meng. Go ahead. We had one question online. Maybe not. Well, I know Jen has a few announcements. Did you have any questions, Jen, before we go into the announcements? Ravi is back. Go ahead, Ravi.
Hi, my internet connection is not so good. So I have a question about the ideal case, ideal system layout, which you showed. In case if we directly couple the solar with the electrolyzer, DC to DC, and we don't have any power converters, then what do you think the system output of solar will be? Because as far as I know, inverter plays a major role in solar plant, and if we're directly trying to couple the load matched electrolyzer to the solar system, solar plant, then the inter-array cables and inter-array voltages needs to be matched with electrolyzer. And we're also removing the overloading advantage. So overloading advantage and inter-array cables mismatch will be there, and I think that adds that removes.
Yeah, certainly there's a concern about if you take out the yeah, and there's a concern about with a power converter, how do you control the voltage? Now, a couple of points here. We are in the mid process of building a small solar electrolyzer based on this system concept, direct coupled with load matching, and we have the electrolyzer. So there's a design issue involved. The voltage of a solar panel does not change more than, say, 10% throughout the day. It's the current which goes from 0 to maximum and then back to 0. So it's really the current which changes a lot. So, and then on the other hand, the electrolyzer actually can handle a wide range of voltage. It's not a one voltage, fixed voltage device. if you look at its polarization curve, actually you can go from about 1.7, 1.8 volts all the way to about 2.5 volts. So that's a very wide voltage range. So that's kind of unique with electrolyzer. Now, of course, the higher the voltage, the lower the system, the electrolyzer efficiency, and also the higher the current. So you need to put in more power. But on the other hand, it does not. Yeah, you have about a 0.5 to 0.6.7 volts per cell voltage range in which you can operate the electrolyzer. So we should take advantage of that. Otherwise, if we don't do direct coupling and we cannot do DC-DC coupling, so the only thing is AC coupling, then we just lose a huge amount of solar energy in doing that. So yeah, I did not mention it. We are reducing the system cost by about 15 to 30%. We're improving system efficiency by about 30%. So we're cutting down the levelized cost of electricity, solar electricity by about 50% in this case. For now, hydrogen electricity cost is a big part of the overall cost. So that's our answer to how to reduce the cost of hydrogen.
Understood. Yeah, thank you.